So you have a 35 right here. So if you look at it, the x is to the left of 35. So since it's to the left of 35, this x value, we should know it should be smaller than 35. So any answer that we get, we should know it should be less than 35. So if you get an answer that's bigger than 35, well, you should already know that's wrong because since it's in the bottom 25%, we should be expecting it to be smaller than 35. So up next, we're gonna go ahead and do, we're gonna go ahead and use Class Calc. So if you have Class Calc, bring it out for that way. You could go ahead and use that. Let's see. Let's see, Class Calc. There we go. All right, so there's Class Calc. So the first thing what we want to go ahead and do, we want to hit the stats button. So first hit stats. Once you hit stats, you want to go here where it says distribution/plot. And then what you want to do, you want to put normal distribution. Any question on how to get to normal distribution? All right. So the first thing I want to go ahead and do, I want to go ahead and enter the mean and standard deviation. So if you remember, the mean was 35. If you remember, standard deviation was 5. And you want to close that off. All right. So right now we're telling our calculator that we're doing a normal distribution and the mean is 35 and that the standard deviation is 5. So now what I want to do, I want to tell the calculator, I want to find the x value that corresponds to a percentage. So to do that, we're going to go again to stats. We're going to go distribution/plot. And we're going to use the inverse CDF. So let's use the inverse CDF. And if you look at this one, what was the percentage that we wanted the bottom toe to be? So what was that percentage? Well, if you remember, the percentage was the bottom 25%. So we put 0.25. And if you look at it, it gave us the answer 31.63. And that's it. So we get 31.63. Cool. Thank you, Daniel and Edgar. All right. But that's it for A. Any question in regard to how we did A? Okay, so I'm going to switch over back to my iPad for that way you can see the lecture. All right. So for part B, if you look at it, it says find the x value for the top 25%. So this one, we want the top 25%. So we're going to redraw the normal distribution. You're going to put 35 in the middle. But for this one, we want the top 25%. So that's this portion here. So we want to find what is the x value that value the bottom 75%, the top 25%. So we want to find what is this x value over here. So if you look at the middle is 35. If you look at the x value is to the right of 35. So I should know that x should be bigger than 35. So for Class Calc, you always have to give it the probability of the left side. So we have to give it what this probability is. Because the thing is, if I give it the probability of the right side, it's not going to give me the right answer because it's always expecting you to give it the probability of the left side. So if I know the probability of the right is 25%, what's the probability of the left side?
75.
That's 75. So you put 75%. If you do 100% minus 25%, you get 75%. Thank you. All right. Everybody good with this drawing? Okay, so I'm going to switch over to class calc. So class calc, here we go. All right, so I'm going to do this all over again. Even though I already have this information here, I can just change it, but just kind of get you comfortable with doing it. So we're going to say stats, distribution, normal distribution. We say the mean is 35, standard deviation is 5. We don't want to find the probability, we want to find the x value, so that's why we're going to do inverse CDF. So instead of putting 0.25, you put 0.75. And now if you look at it, give us x is equal to 38.37. So we'll say 38.37. All right, and that's it for part B. Any question in regard to part B? So just remember, if it's the top percentage, you always give the probability to the left side. If it's a bottom percentage, well, you already have the probability to the left side, so no need to find it. So let me switch over back to my notes, and that way we'll do a second example.
Wait, why is it 38.37 if you need to find the top 25?
All right, let me go back. Well, so you're saying why is it 38.37?
Yeah. Why is that the answer? Like, wouldn't you, wouldn't you subtract that by 100 because you're trying to get the top 25%?
Well, technically, I already did that because pretty much when you say 0.75, you're technically telling the calculator or class calc that you want the top 75%, or sorry, the bottom 75%, which is the top 75%.
Oh,
So once you tell a 0.75, the calculator automatically know you want the top 75, the top 25%.
oh, okay.
Yeah, because the thing is, the calculator, it does have like some limitation that it always wants the probability to be at the left side. So if I know the probability of the right side 0.25, in order for me to tell it, give me the top 25%, I have to tell them the probability of the left side is 0.75.
Okay.
All right. So let's do this next one. So for this next one, you do kind of want to think about it a little bit. So for this one, says a lifetime of certain brand of tire is approximately normally distributed with a mean of 42,500 miles with a standard deviation of 3,200 miles. What warranty should the company use if they want 88% of the tire to outlast the warranty? So first, they kind of just put something that we know. So we know the mean is 42,500. I know standard deviation is 3,200. So those are two things that they give me. So they give me the mean is 42,500. Standard deviation is 3,200. Everybody okay with that?
Yes.
All right. So let's go ahead and draw this. So we put 42,500. All right. So for this one, we want 88% of the tire to outlast. So we want 88% of the tire to outlast the warranty. So what does it mean if they outlast the warranty?
They didn't pop.
Yeah, so they didn't pop. So if they didn't pop, that's essentially a good thing because that means that the tire lasted a certain amount of time, correct?
Yeah.
So what side should I say? So if the tire lasted a certain amount of time, would I say this is my 88%?
The other side.
Or should I say this is my 88%?
The right.
Yeah, so we want the right because we want 80% of the tire to outlast it. So that means what percentage of tire do we not want to outlast the warranty?
It can't be. What's
So,
that minus?
so how many tire are actually you are going to use the warranty?
12%.
12.
12%. If you kind of think about it, we only want to have 12% of the tire to actually need to use the warranty, and then we want 88% of the tire that they outlast the warranty. So that means you don't get to replace your tire because they actually lasted longer than what the warranty guarantee. So for this one, we have to find how long of a warranty should we give them in order for that way 12% of the tire actually use the warranty, but the other 80% of the tire don't use the warranty. Everybody kind of go with that idea?
Mm-hmm.
Okay, so up next we're gonna go ahead and do, we're gonna go back to class cal. And after this, I'll show you how to do this if you're using a TI-83 or 84. So we're gonna go to stats, we're gonna go to distribution, we're gonna go to normal distribution. So our mean is 42,500. Standard deviation is 3,200. But for this one, we want to find the x, so we use the inverse CDF. So we say stats, distribution, inverse CDF, and we want to put the probability of the left side, which is the 12%, so we put 0.12. And if you look, we get 38,740.04. And that's it for the other example. Any question in regard to that last example?
No.
Okay, so I'm gonna show you if you have a TI-83. So if you're using class calc, just ignore this. That question is for the one about the tire, Brianna. Okay, so if you have a TI-83 or 84, you go to second, bars, and you want to do number 3, inverse norm. So the area, you put 0.12. The mean is 42,500. And lastly, standard deviation, 3,200. You press paste, you press enter. And if you look at it, it'll give us exactly the same answer that we did that when we did it using ClassCal. Any question in regard to people using the TI-83 or 84? All right. So let's go over and do a couple of more examples in case you still need some more practice. All right, so for this one, says the resting heart rate for a healthy adult horse average 46 heartbeat per minute with a standard deviation at 8 beat per minute. A horse's resting heart rate is in the upper 10% of the distributional heart rate, may have a secondary infection or an illness that needs to be treated. How fast must a healthy horse heart be beating to fall into this at-risk group? So first let's find the mean and let's find the standard deviation. So for this problem, what is my mean?
46 heartbeats per
Yeah.
minute.
So I put 46. What about standard deviation?
8 beats per minute.
Cool. Yeah. All right. So right here, we're going to put 46 because that's the mean. If you look at it, it says a horse whose resting heart rate is in the upper 10% of the distribution. So the upper 10%, would that be the left side of 46 or will that be to the right of 46?
All right.
The left.
Well, since it said upper is another way of saying the top. So that should be the right side. So now what we want to go ahead and do, we're going to want to find this x value. So we want to find what is the x value that corresponds with that top 10%. So if we want the top 10%, how much percentage is below 10%?
90.
90. And the reason why that's important, because just remember for your TI-83 or for class calc, it always wants the probability of the left side. So we want to give it 0.90 versus 0.10. All right. So one thing you should notice for x, since it's on the right side of 46, that means it should be a number bigger than 46. So if you get a number that's smaller than 46, then you know you did something wrong because the x value should be bigger. So right now we're going to transition over to class calc. All right. And also, like, if you don't want to go through all of the steps, you can just go back here and you can just start editing it. Oops, I edited a little bit too much. So we could go right here. We could change that to 46. For standard deviation, switch it to A. And then for the area, you put 0.90 and you get your answer. So that way you don't have to constantly be entering the same thing over and over again. So your final answer, if you look right here, you get 56.25. And that's it. Or you could put 56.3. All right, so I'm going to go back to the iPad for that way you can just see the answer. All right, so you get 56.25. Any question on how we got 56.25?
No.
Okay. So what I want you to go ahead and do, I want you to go ahead and do this next problem. So I want you to just do A and we'll do B together. So just remember A is exactly what we've been doing, nothing different than what we've been doing for the last 3 examples. Cool, good job. Yeah, it should be that answer. All right, so let's try entering this. So for the normal distribution, the first thing you gotta do, enter the mean. What do we get the mean to be?
50.
50.
50. And then what do we get a standard deviation to be?
10.
Yeah. And for this one, what should we say the area to the left is?
90.
Yeah, 0.90. So if you do all of this, you should get the answer of 62.82. So in order for somebody to be eligible to be hired by the agency, they have to score a 62.82 or higher. And that way they'll be in the top 10%. All right, everybody good for part A? Yeah, anytime they say top percentage is always on the right tail. If they say bottom percentage or percentile, then that mean is on the left tail. So if they say top percent, you should automatically know it's on the right tail. If they say bottom percentage, it's automatically in the left tail. All right. So let's do part B. So for part B, it said those officers scoring below the 20 percentile is sent to undergo additional training. What is the minimum score needed to avoid this training? So anytime they want you to find percentile, this is the other way of saying the bottom. So if I say 20 percentile or bottom 20%, the bottom 20% is exactly the same thing. So for this one, if we draw this out, you should put 50 in the middle, and we want the bottom 20%. And we want to find what this x value is equal to. So the good thing about this x value, well, you know it should be smaller than 50. So the way we want to do it, we're going to say normal. Well, actually, you're going to do this. The only thing that's going to change instead of it being 0.90 is 0.20. And if you do that, you should get x is equal to, let me get some red, 41.58. And that'll be your answer for part B. Any question for part B? All right, so let me scroll down. All right. So we're gonna do one more problem just to make sure that you definitely get this. So for this example, it said, consider baby born in the normal range of 37 to 43 week gestational age. Extensive data support the assumption that for a such baby born in the United States, birth weight is normally distributed with a mean of 7.56 pounds and a standard deviation of 1.06 pounds. So they're telling us mean is 7.56, standard deviation is 1.06. So for this problem, it said, how big does the baby need to be if we want them to be in the top 1%? Oops. So you put the mean in the middle, and we want them to be in the top 1%. So we want this right here. So we want the top 1%. So we want to find what this x is equal to. So once again, we're gonna go ahead and we're gonna go ahead and you find this. So for a change of pace, I'm gonna do this using the TI-83 or 84 calculator. So that way those students don't feel left out. So we'll put second bars. We'll do inverse norm. If you look at the area, since I want the top 1%, what percentage should be for the left side?
$99.
Yeah, 0.99. So you put 0.99. If you look at the mean is 7.56. Our standard deviation is 1.0. And we press enter. We press enter again. And you get the baby has to be 10.03 pounds in order for that baby to be considered in the top 1%. So for a baby to be in the top 1%, that baby must be weigh either 10.03 pounds or higher. All right, that's it for A. Any question in regard to A? All right, so let's do B. So it says, how small does the baby need to be if we want them to be in the bottom 4%? So right here, we want the bottom 4%. So we'll say this is 4%. We want to find this X value. We know the middle is 7.56. So if we want the bottom 4%, the only thing we're going to change, all you're going to do, you change the area. So instead of saying 0.99, so if we want the bottom 4%, you put 0.4. You press enter, and you should have gotten 5.7. What do you say, 5.7? And that's it. But that's how you want to do part B. Since we're looking for the bottom 4%, there's no need to find the probability to the left because we already know the probability to the left is 4%. So that's it for B. Any question in regard to B? All right. So I'll leave this one for extra practice in case you still need a little bit more to practice on. But I think hopefully by now you kind of get the point of this one. So up next, we're going to get into 6.3. So for 6.3 is the distribution of a sample mean. So for a distribution of a sample mean, we're not doing a random selection anymore. What we're actually going to do, we're going to be doing a random selection of n many people. So when we say n many people, that means instead of our sample size, because in this case, n was always equal to 1. Now what we're going to be doing, we're going to be doing a sample size greater than 1. So if we're doing a sample size greater than 1, would that represent that we're going to have a new mean and a new standard deviation? And this standard deviation, another term that they call it standard error. So if I say standard deviation of a sampling distribution or standard error, both of them are the same thing. So let me put the second one. So both of them represent this. So this is called standard error or standard deviation of the sampling distribution. So for this one, it shouldn't really affect our answer for that much. Like the only thing we have to do, we have to adjust the standard deviation because now since we're taking a sample size greater than 1, we now know that the mean will still stay the same, but for standard deviation we will have to adjust it. So the new formula for z-score is going to be equal to that, but since we're using ClassCalc and since we're using the TI-83, we're not really going to use this formula. you'd have to adjust the function in your calculator. So let's do a problem. Oh, sorry, before we do a problem, let's do the central limit theorem. Okay, so for the central limit theorem, we only want to use the central limit theorem when we don't know our data set is normally distributed. So on tests or quizzes, I'll usually ask you, can we apply the central limit theorem? And pretty much you have to tell me either yes or no, and you tell me why yes or no. So for the central limit theorem, we only apply it if we don't know our data set is normally distributed. So if our data set is normally distributed, then there's no need for the central limit theorem, because the central limit theorem, we only use it if I don't know our data set is normally distributed. If my data set is not normally distributed, that's when you want to apply the central limit theorem, because the central limit theorem says that as your sample size increases, our distribution should become more and more symmetric or more and more normal. So usually the rule of thumb that we're going to use the sample size of n is equal to 30. So if n is greater than or equal to 30, we say is approximately normal. If n is smaller than 30 and we don't know our data set is normally distributed, then we're going to say it's not normal. But usually the rule of thumb, if n is greater than or equal to 30, we say approximately normal. Everybody kind of go with that? All right. So let's go on some pictures. All right. So for these pictures, it is saying our data set in the beginning is normal. And what we want to do, we want to see what's happening as we increase the sample size. So if our data set is normal and if we increase the sample size, if you look at it, the data set is still going to be normal. So if our data set is already normal and we start randomly selecting from that data set, any histogram that we create using that data set should also be normal. So that's what the second and the third picture is doing. So you're saying if we randomly select from a normal data set, our data set that we create using that normal data set should also be normal. So let's go on to the second example. So if I look at this data set, is that data set normal? So does it look like a bell-shaped curve?
No.
No. So we'll say not normal. But what about this graph? Does this graph kind of look normal?
Kind of.
So we'll put kind of normal. What about this graph over here? Does that one look normal?
Yes.
Yeah, so we'll say approximately normal. So this is what the central limit theorem is saying. It is saying even though we don't start off with a normal distribution, if we take a big enough sample size, our data set that we get from the sample size should be considered to be normal. All right, so let me show you, I think, one or two more. All right, so if I look at this, is this graph normal?
No.
No, so we'll say not normal. But what about this one over here? Does that one look normal? That one's normal. So once again, because if we start off with a data set that's not normal, but if we keep on getting a sample size of n many, the distribution of the sample size of n many should be considered normal. So it is saying if we keep on sampling from it, the new distribution that we're creating with that new sample should now be considered normal, and that's because of the central limit theorem. All right. Everybody kind of go with the idea of the central limit theorem?
Yes.
Okay. All right, so let's scroll down. Cool. And this is just kind of like a recap. It is saying it doesn't matter if your data set is skewed to the right, uniform, a U, or skewed to the left. If we take a big enough sample size, the new sample distribution with that sample size of n many should now be considered approximately normal. All right. So let's do our very first problem. So up next, what we're going to do, we're going to describe the sampling distribution of a sample mean. So for this one, anytime I ask you this for a test or the quiz, I'm going to want three things. So the three things I want is mu of x bar, sigma of x bar, and I want you to tell me if the data set is not normal, normal, or approximately normal. So this is the three things that I want. So anytime in a test, if I ask you for this, I just want you to give me these three things. All right, so let's go ahead and do the first one. So first one we want is mu of x bar. So we want mu of x bar, which mu of x bar is equal to mu. What is mu in this case scenario?
20.
Yeah, so mu is 20. So that's it. You have to tell me mu of x bar is equal to 20. Because mu of x bar is equal to mu, and mu is equal to 20 in this case scenario. Up next, what we want to do, we're going to find standard error. So the formula for standard error is sigma divided by square root of n. So that is the basic formula for that is always going to be standard deviation divided by square root of n. So we're going to get standard deviation, which is equal to 12 divided by square root of n, which is square root of 9. Any questions so far? I got 12 divided by square root of 9. So if you do square root of 9, you actually get 3. So if you do 12 divided by 3, you get 4. Perfect. Thank you, Brianna. So that's standard error or the standard deviation of the sampling distribution. So the next thing what we want to do, we want to say if this is not normal, normal, or approximately normal. So for this one, what do they tell us? Do they tell us the data set is normal?
Yes.
Yeah. So your answer is it's normal because they tell us it's normal. Oh, oops, wrong one. Right. And that's it for A. So those are the three things that you want to give me if I say find the sampling distribution. Any question in regard to A?
No.
All right, let's do B. So if you look at B, B said describe the sampling distribution of a sample mean for mu is equal to 20, sigma is equal to 12 for a sample size of 100 if the sample comes from a skewed distribution. All right, so first thing we're gonna go ahead and do, we're gonna find mu. So in this case, what is mu?
20.
20. So that's your answer. standard deviation of the sampling distribution is standard deviation divided by square root of n. So standard deviation is 12, but how big of a sample size do we have now?
100.
100. So if I do 12 divided by square root of 100, what do we get?
1.2.
Yeah, 1.2, perfect. All right, so that's our mean of X bar, and that's our standard deviation of X bar. Any question I got either one of those two as answers? Okay, so up next, we're gonna say, is this non-normal, normal, or approximately normal? So you first want to check to see if this is normal. If it's normal, like the last prompt, it will tell you if it's normal. Do they tell us this distribution is normal?
No.
No. If you look at it, they actually say it is a skew distribution. So you should already know it's not normal. Because in order for it to be normal, the problem has to tell you it's normal. So right now, what we're gonna do is either gonna be non-normal or approximately normal. So if our data set is stays like this, we're gonna say it's not normal. To see if it's approximately normal, we have to apply the central limit theorem. So to apply the central limit theorem, we have to check the condition that n has to be greater than or equal to 30. So for this one, if you look at it, what was my n? What was my sample size?
100.
100. So is 100 bigger than or equal to 30?
Yes.
So since 100 is bigger than or equal to 30, we're gonna say this is approximately normal. And that's how you wanna apply the central limit theorem. The central limit theorem is say, if I know my distribution is not normal, we could say the approximately normal as long as our data set or our sample size is big enough. All right, but that's it for B. Any question for B?
No.
All right, so let's do C. So for C, it said, what do you notice? So what you kind of notice is different from A and B.
That the bigger your sample size, the more skewed your distribution will be.
Well, you can have a big sample size, but that doesn't mean that your distribution will be skewed. It depends like what type of distribution you're sampling from. So if it doesn't have like whether it's skew or normal has nothing to do with your sample size. But what like one thing that we kind of notice about the standard error? Like what happened to the standard error? Because in one standard error we got 4, the other standard error we got 1.2. But for both of them, we had a standard deviation for a 12. So the standard error went down. Well, why did the standard error go down though? Like what happened to cause it to go down?
There was a bigger sample size.
Yeah, good. So the standard error went down because the sample size was increased. So yeah, so kind of think about it, like the bigger the sample size, the smaller your standard error should get, because the bigger the sample size get, like the more accurate it should be, because the bigger a sample, like the more accurate that sample should be versus a sample size of 9. So kind of think about like which sample will you trust more? A sample which only has 9 or a sample that has 100? Well, you'll trust more the sample that has 100 because the sample that has 100 is more accurate compared to the sample size that only has 9. And that kind of go back to the standard error, because it's saying if we have a sample size of 9, the standard error is 4. But if we have a sample size of 100, now my standard error is 1.2. So you're saying the bigger the sample size is, the smaller the standard error should be, because it should be more accurate. All right, but that's it for the last problem. Any question for the last problem?
No.
So let's scroll on down. All right, so what I want you to do, I want you to practice on this next one. So take a minute and practice on that one. In case you forgot it, find mu of x bar, actually. So go ahead and find those 3 things.